Are we on? We are on, thank you. Okay, can you take your seats? I see people loitering around a little bit, and I know conferences are all about talking to each other and loitering a bit, but it is time to take your seats because we've got a very exciting talk coming up next. He's been released back into the wild after a little bit of a hiatus that some of us had to endure, but now he's here to talk all about React Native. Let's give a very big ComCon round of applause to Saúl from the Jitsi project.
Thanks, David, and thanks everybody for coming here today. I've learned from Jared earlier this week that I should introduce myself properly. So, hola. My name is Saúl. I come from 8x8, and I work on Jitsi, React Native, WebRTC, and some other projects. You might have heard me talk about Jitsi many times in the past, and today I'm going to talk about React Native, WebRTC, which I think is the biggest project we maintain outside of outside of the Jitsi organization. So hopefully you learn something. Before I start, I want a quick show of hands. Who has worked with React Native before? All right. For those who have not, who knows what it is? And who has not raised their hand yet? All right. The couple. A quick recap. So React Native is this mobile framework developed by Facebook that allows you to write mobile applications in JavaScript that will then run as native because they create native views and native components. Now, being this sort of environment different than a browser, it does not have all the browser APIs that we're used to, one of which being WebRTC. And React Native WebRTC is the plugin that provides the WebRTC API as seen in browsers, but for the React Native environment. It was started in 2015 by Howard Yang, and just for those of you who have used React Native, this was the React Native 0.11 days. So it's been around for a little while. Jitsi started contributing in 2016 because there was a concerted effort to move our code base to React. It was like jQuery plugins in the past, and also share it with a mobile code base and go React Native. That was the direction that was set. And in 2017, I joined the Jitsi team and took over the maintenance of that library. I'm going to talk a little bit about my past in maintaining such libraries. And since 2019, it sort of became a community project. We created a GitHub org for projects that are ancillary to React Native WebRTC, like in-call manager, call keep. They are all tools that you probably want to use if you're building a calling style application with React Native, and they're under the same umbrella organization. And yeah, we banded together and developed it with some other friends from the industry. So let's look at how a React Native project, and particularly React Native WebRTC, is sort of structured. Usually, if you need to wrap a native library, you're going to have a little bit of Java or Kotlin to talk to the Android side of things, a little bit of Objective-C or Swift, and then some JavaScript or TypeScript to tie it all together and expose that API to the JavaScript side of things. We implement the WebRTC API as seen in browsers, as I said, and we wrap Google's WebRTC implementation. There's others out there, but we're wrapping that one because it does expose an Objective-C API and a Java API, so we can wrap those for React Native. And the project follows the same versioning as Chromium, so if you see like the latest release is React Native WebRTC 111.0.1, that means that is using Chromium's 111 released WebRTC version. Generally speaking, the blocky architecture looks a bit like this. From the bottommost layer, WebRTC is mostly a C++ library. Then within their code base themselves, this is inside libWebRTC still, they've got Java bindings written with JNI, so a tiny bit of C glue, and then the Objective-C bindings, but you can use Objective-C++ to talk to C++ directly, so it's like a thinner layer, let's say. And then on top of it, we're going to layer our React Native API or wrapper, both on the Objective-C and on the Java side. And then just on top of it, we throw in some TypeScript, and that's the API that you're using. So if you want to build something like this, you first need to build WebRTC. So how hard can it be? I've been doing this for a while because before I was doing React Native WebRTC, I was working on the Cordova iOS WebRTC plugin. which was written in Swift. Same thing, wrapping libWebRTC to expose the WebRTC API to Cordova applications. And things have progressed for the good, which is nice. So WebRTC uses the same build system as Chromium called GN, or Generate Ninja. And today, the entire toolchain is downloaded with Depot tools, which is a helper that Google provides for building Chromium and the ancillary projects. It has been very stable since around M100. So before that, for example, the iOS toolchain was using Xcode in your machine that you were doing your builds, but Android was using the Clang version that Depot tools download. Now it's all gotten directly from Depot tools, so it's a very sort of self-contained toolchain, and it is I would say is independent from the environment, which makes it very consistent and nice to work with. They provide scripts for creating your Android builds and your iOS builds. For tiny shenanigans, I wrote some Python scripts so that we could make the builds. So for React Native WebRTC, those are up on GitHub, but you could use the supplied ones by Google just as fine. And an important aspect is that there are no official build artifacts by Google anymore. There haven't been for a few years, which is not a bad thing because there are a bunch of things you need to tweak at compile time. And that basically means that I don't think there can be a universal WebRTC build. Each one may want to turn some knobs. Speaking of builds, has anybody had the misfortune of having to deal with bitcode? Just me? Jeez. So Chad made this nice image for me when I wrote an article for WebRTC Hacks. Long story short, there was a very tumultuous period in building WebRTC while Google was changing toolchains, but Apple was still not deprecating bitcode, and the builds were big, and you needed to patch WebRTC to use the other compiler. All of that is gone now. Apple deprecated bitcode with Xcode 14, so the Depot tools toolchain works great, and so you don't need to know about this. But if you're curious, in WebRTC Hacks, you can find the article, which it was a fun, investigation. So for React Native WebRTC, we use the Jitsi builds, let's say, and they're usually lag a few versions behind the stable Chromium for stability purposes. Like, we don't want to release it as they release and, see how it breaks. On Android, we also make the builds available on Maven Central since pretty recently, and on iOS, it's available on CocoaPods and has been for a while. The reason I mention this is because if you want to build a pure native WebRTC application and you don't want to bother with making your builds because you trust me very much, you're very welcome to use these builds because I made them this way so they can also be reused by the community for projects other than React Native WebRTC. We strive for mostly a vanilla build, so as little customization as possible. However, there is one patch that Chromium will never accept, but I got most of it there, and which is the built-in certificate authority list. So by default, libWebRTC can only make turn TLS connections to Google. And when you need turn TLS, you really need turn TLS, because it means nothing else worked. So you really want that to actually, connect. So I made a patch so that you could generate the code that embeds all those certificate chains, but take them from the Mozilla CA store. And Google accepted that part of the patch, but not the part where we actually take the Mozilla thing and embed it. They don't want to have a list of CAs. I understand why. And as I said before, we need to do our own builds, so it doesn't matter. It doesn't matter. It's one extra step. We run it at build time, generate that header file, embed it in the build, and Bob's your uncle. That's where we keep the tree where we do the builds from. And it's, Trust Me Bro certified. So if you like them, they are made artisanally by yours truly. Let's dive a bit into the native SDKs, the object model, and how we glue these things together. So as I said, the way the libWebRTC works internally is it's got these two completely separate parts, the Objective-C side, the Java side, that both wrap their C++ counterparts. Some APIs that you see in the browser are not actually part of libWebRTC. They are implemented in Chromium. So those we will need to recreate. For example, get contributing sources is not a thing that libWebRTC exposes. It's something that they built in Chromium. And some of the APIs are close enough, but not quite what the web APIs are. And so part of the work in building such a library is to sort of reconcile those little differences so that applications don't need to make exceptions for, oh, this is React Native, so let's do this. And the API has some very interesting quirks. So, for example, if you get the list of senders in a peer connection, both in Java and Objective-C, you're going to get a fresh list of fresh objects every single time. So you're going to get new Java objects for each sender, which wrap the same C++ object. So if you call it twice, you're going to get fresh objects, but their underlying C++ thing points to the same thing. So you can just compare them. So when you want to store these things, you need to be very mindful. But to make things, so they do offer some methods for comparison, but you need to remember and use them. And to make things a bit more spicy, if you do like media stream get tracks, that doesn't give you a fresh list. It's the same list as before. So it's different than the senders. So you have to dive a little bit deep into how the thing is implemented to not make mistakes. And then why is the track not matched? Well, technically it's the same track, but it's a different wrapping object, so it will not match. Now, that is on the native side of things, but as I said, we need to expose a JavaScript thing. So how do we map these to JavaScript objects? Well, we need to serialize everything, basically, using like JSON. And so then we need to map JS objects with native objects, and we use IDs to match them. And for example, we generate, for things we can generate locally, we can create local IDs for each peer connection, for each data channel, for each media stream. We can generate one locally. But for things that come remotely, it gets interesting. Because in the media stream specification, it will say that the media stream ID has got to be globally unique, unless when the reason is not to. Which means there can be collisions. And there are, and we got reports. So what we do is we create a locally generated, globally unique ID, and we attach it to that object, and that's what we use to reference it. And we refer to this as like the React tag, let's say. And this is what we use also to like render streams. So we call like, oh, I got a stream, I want to render it, so you call like a toURL method of some sort, kind of mimicking the way you used to attach streams to video elements before source object became a thing. And we use this React ID to identify them. So the challenge is to keep all of these in sync. And now, after the years, I think that we could actually do a little bit better in the mapping. Instead of having something completely unique, which means sometimes debugging could be a bit more difficult, we could, because remote streams are always tied to the peer connection they came from, and the peer connection has a unique ID. So I could create a unique ID, which is the peer connection ID plus the media stream ID, and that we know like it will be fully unique. But it's kind of a quality of life improvement, so maybe we'll get there one day. This is like an example. For instance, when you do get user media, you're going to get like the stream ID, the stream React tag, and an array of data that represents a track. And just like that, we're going to build all these JavaScript objects that represent what's done in native. So you got like a Matroska-style situation where JavaScript wraps Objective-C and Java wraps C++, wraps the platform layer, wraps. So I said we do implement standard WebRTC APIs, except when we can't, or we have good reasons not to. And the first one, for instance, is object lifetime. So when a peer connection gets closed, all the remote streams will disappear. But what about the local ones? Because you can use a stream outside of the context of a peer connection. And in these APIs, you don't have a way to latch onto the garbage collector, for instance, and say, well, when this object disappears, I want to destroy the underlying stuff. You can't do that in React Native today. So we have the mediastream.release function that allows you to release a track. And at that point, it's completely dead. All the underlying resources have been freed, and there's nothing else to do there. The toURL method, as I mentioned, it's something that you use to attach to a view effects for video, like blur or something like that. And then you can set them from JavaScript just by name. So you register them in native, you use them just by name. And because one of the differences between native and the web is that in the web you would render an audio track by putting it on an audio tag or with web audio. But in the native WebRTC library, it just plays. That's what it does. So in order to set the volume of it, we added an extra API that you can use to set the volume of a given track so that you can tweak that a little bit. Now let's look a bit at how now we got the objects, we know what we're wrapping, let's tie it together with React Native. And this is a bit about what's currently called legacy React Native architecture. So in React Native, you will have your JavaScript thread, which generally speaking, it runs JavaScript core, so the same sort of JavaScript interpreter you can find in Safari. It loads your JavaScript, and then all of the method calls will actually go through this thing called a bridge. And in the UI thread, you are going to have your native UI and your native modules, which can also run in different threads. And then the shadow thread, which one's yoga, is the layout. So that computes the layout, and then there is a bunch of synchronization going on in between all of these three things. The important aspect about this is that your React Native modules, all of the APIs are asynchronous. However, in the WebRTC world, not all the APIs are asynchronous. For some reason, I find hard to understand, create data channel, add track, add transceiver don't return a promise. They expect to return an object right now. So how do we return an object if we have an asynchronous model where we're not able to create it on the spot? Well, it turns out that there is a way. In the past, what we were doing was faking it, so creating it asynchronously and then figuring out a way to return an error event or something. But that broke really quickly. So there is a way to actually do synchronous calls. It's kind of frowned upon, but it's possible to do it. And unless you're doing it in a hot path, it's just OK. And nobody's going to call add transceiver a million times in a loop. So it's kind of fine to do. And we're using it in like 7 of the APIs. As I said, all of those 3, create data channel, transceiver, add track. Because of the expectations are that you receive a thing, we chose to compromise and say, well, this API is not ideal, but it won't hurt because this would likely never be in a hot path. And we fulfill the expectations of the user, which is that it behaves exactly like a browser. But there is more threading fun stuff to be had. WebRTC has sort of 2 important threads to be aware of, the signaling thread and the network thread. So when we call into WebRTC, we do it from the thread where the React Native module is happening, which could be part of a thread pool. But when WebRTC calls into us, like when you say, hey, set remote description, and then you pass like a callback and it tells you, I have set it, here it is. At that very point, that callback happens in the WebRTC thread, not in your thread, of course. So we had to add a queue, which is it's a single thread where all of the WebRTC operations are serialized. This allows to also fulfill kind of the contract. If you read the WebRTC spec, it says a lot about chain this operation in the da-da-da-da-da. So, and things like that. So if you call one API, then you call another, the expectation is that, of course, the operations run in that sequence. And we do that by serializing them in this operations queue, and we also serialize handling of these callbacks that come from WebRTC. Now let's look at how the project is doing, and how it's doing. So we're running WebRTC 111 as of this month. It's a unified plan only, so because unified plan 1, we decided to implement just that when we migrated away. I'm going to talk about it on the next slide. We migrated the project to TypeScript, which made actually working with it better going forward. Not 100% of the APIs are implemented, but the most used ones are. And if you're trying to use in this plugin and you run into, hey, I really need this, please do reach out to us, and I'm sure we'll figure out a way to help you contribute that commit. One unfortunate thing is that the buzz factor is mostly one, aka me, but we got some help, which is pretty good because these 3 people were not involved just a handful of years ago. Jonathan Weaver has been helping a lot with, onboarding users, bug triaging, and also patches. David Liu from LifeKit, and shout out to LifeKit because they stepped up the contribution even to a point of, I need this API, but it's not wrapped in Objective-C and Java, so contributed to WebRTC to add that API, and then the React Native patch to expose us that API to JavaScript. And then Mr. ComCom himself, wherever he is, has been also helping out in the project, sending patches, closing bugs and responding to people. If you want to get involved, please do. I promise we're nice people. So I said we're in unified plan now. I want to briefly talk about that. It was the largest change that the project went through since its inception, I would say, because the React Native API has been mostly stable. It took a while to get there, and one thing I think we did right was to drop Plan B in the process to reduce the complexity. So we went cold turkey from one plan to another, changed the major version of the project, and then this way we adjusted people's expectations. I think the first beta of it was in September, and the first release in December last year, and we couldn't have done it probably without the help of Dolby. My good friend Sergio, who was working in Millicast, acquired by Dolby, reached out and said, hey, we need unified plan. I can give you a developer. Can we work together? I said, excellent. So you see if they work with us. He made the Android bits and a bunch of other stuff. We worked on iOS, met in the middle, added a bunch of JavaScript things, and yeah, it was great times. One interesting thing that we found during the unified plan migration was this one-liner patch that I had to make. It's just a mapping from a transceiver state into Java. But this sort of told me that nobody is using the Java SDK in a serious manner. Because if you did get transceivers on a peer connection where one of the transceivers was stopped, your app crashes without this patch. Because there is no way to map the C++ enum to the Java one. So I'm like, who is using this other than, well, us? It's a good question. And on-track shenanigans. It's another interesting thing that came up while doing the unified plan migration. So as probably know, on-track is sort of the unified plan's primary API where you receive remote tracks. And the thing is, there's like 3 APIs in native. None of them quite match the semantics that you need, to the point where not Chrome, not Safari that uses WebRTC are using it. So why it exists is interesting. And there's a lot of subtleties, like, for example, when you do set remote description, promise is not resolved, on-track fires, and if you look at the remote description, what you expect to see is the new one. But it has not resolved yet. So we needed to get that just right. So that's why the first beta was in September and the release in December. It was a lot of getting all these shenanigans right. So I want to talk a little bit about the challenges that the project has gone through, if you will, because, yeah, I think is relevant if you're tackling a similar project. So testing is an interesting conundrum. We don't have any form of automated testing. I'm not sure, like, I would really want to hear if someone has suggestions. The problem is, many of the issues that you run into in the real world are really hard to sort of reproduce. So we could add some test that creates a data channel, some peer connections, yada, yada. But how can I debug my screen is black? Like in a test. Like, first we would need real devices because you can't test everything in the simulators. And then how to actually know that that validates all the problems is, I think, is pretty challenging. So for the most part, we rely on our community, on the people that use the plugin. We rely, of course, heavily on our own users. In this case, I mean Jitsi. So our millions of users running Jitsi Meet, well, we have an open beta, and we got Crashlytics, so I've fixed numerous bugs just by looking at the crash logs without actually knowing what failed. But I'm like, well, Android SDK does not say this API can fail. Turns out it can. So might as well fix this and that. So I'm going to talk about upstreaming in a sec, but that's how I started contributing to WebRTC, was shielding a lot of APIs that apparently could not fail, except they could, or for certain manufacturers, or for certain phases of the moon. There was a lot of that going on. So if anybody has some suggestions on how we can improve the testing process to sort of validate all these APIs, I'd love to hear it. Some interesting challenges also come from the video rendering side of things. So we will get occasionally the report of, my video is black. Well, that's great. So how about your turn servers, your stand servers? Is there an ICE problem? Because one thing we've seen, contrary to what I thought, so I thought that the people that would use our plugin were, you guys. People using WebRTC and then needing a mobile app. Turns out I was totally wrong. Most of the people using our plugin, or at least the ones I've interacted with, are people that know nothing about WebRTC. They're working on something else, and they need to add some real-time communications capability to their app, and then it's like, oh, WebRTC seems to be the way to do it. So their first entry point into WebRTC is this thing. And then it all gets confusing, because we're wrapping WebRTC, which means where's the documentation? Well, in MDN. I don't need to document what's already documented, do I? So it creates these interesting things, and sort of trying to explain stun, turn, ICE, it can be challenging, because rendering problems could be in many places, right? And one such place, for example, so Android is not my favorite platform, as my friends know, and we render using OpenGL, and you can create a number of EGL contexts, but you don't know how many, and you will only know when you crash to create one. And recovering from it is sort of, what do? You're not going to be able to render anything. So that's a problem. Hardware codecs crash sometimes, and there is no great way to recover from it either. So one of the things we learned during the pandemic was we actually tried to use hardware decoding, and then it failed on a ton of Samsungs, so disable it on Samsungs, then failed on a bunch of Huawei, so disable it for Huawei. Then it's like, I give up. If it doesn't work on 2 of the 3 major manufacturers, might as well not use it. So, and then another thing is that people using this plugin expect, for instance, for simulcast to work, right? Why wouldn't it? For instance, it works on iOS. Why doesn't it work on Android? Because the default codecs are the hardware codecs. So I polled the community, the small community that we're participating, and in the last couple of releases, we changed the default codec factories. This is still configurable from your application's perspective, but now we have a custom codec factory that would do H.264 with the hardware codecs and the rest of the codecs with the software codecs. This way, we don't have hardware codec-related crashes, and we can do simulcast. And it's consistent with what iOS does. In iOS, on the counterpart, we were doing metal-based rendering for a long time, but there was like a build time flag to detect support for it. And WebRTC, the upstream project, dropped the flag, but it was nowhere to be found in the release notes. So suddenly, we falled back into not using metal for 2 years until I realized that that flag was gone. Oopsie. So fixed that, and then started to see some interesting crashes, because, metal crashes now. And turns out that when you send some odd resolutions to the metal renderer, like 1 by something, or something by 1, it would crash because it expects those numbers to be even when rounding. So I made a small fix for that, sent it upstream, and it's now fixed. But it was an interesting discovery in the rendering pipeline things. Upstream has also been, and can be, a challenge, because I think the native SDKs are largely unmaintained by Google. So if they change something on the C++ layer, they will make the native APIs work. They are part of their test bots that test compilation and other shenanigans. but I don't think there are heavy users, many heavy users out there. Or maybe they are, and they use some small fraction of the API where things work. But what we've seen is what I sense is that there's no maintenance. However, it's fine, because the community can take on that work. I've sent patches, you can send patches. And I like to shout out a few people here, because Fippo, which you might know from the industry, has been my sort of WebRTC mentor, helping me tap in the shoulder the people that I need to tap in the shoulder to get the patches in, and actually, you know, they got in a pretty speedy manner. Daniel Lee has been helping out with iOS SDK, improving things, also with all sorts of compilation and build time shenanigans in the past. And Yuri has also been helping out with the iOS and Android SDKs. And as I mentioned earlier, LiveKit needed one of these APIs, made a pull request for Android and iOS, and then the React Native wrapper for that. So I think that the path forward is for the community to take on the maintenance of the native APIs as we go there. And there are other projects that depend on them as well, like I think there is a Flutter WebRTC SDK that probably also relies on some of these. So I think it's up to the community to step up. And I have left some time so we can have a little chat and have some questions about wrapping WebRTC. Maybe you have your own experiences, and let's chat about it. Any questions?
Oh, thank you, Saúl. There's one there. Our first customer. I'm going to bring you the mic for the purposes of people looking at the live stream.
We built a web phone using WebRTC with these plugins, well, with Dan's help also. And mine is not really a question, but a request that if you find better ways to test, we'd also be interested. We have the same thing. We've bought a bunch of devices. We're buying devices, manual testing. But the users out there have the variety of devices out there for Android. For our app, supported devices, over 14,000 different model numbers. So so
I have found that at the very least, using, I know some people don't like Google, but I don't think there's anything equivalent to Crashlytics, to Firebase Crashlytics. So that's what we use for tracking crashes, and it's been invaluable because you can see, and right now, for instance, there is a bug in React Native itself with animations in some Android 12 devices that have not applied a patch to the Android version they're running that's like 2 years old. And you see that in your Crashlytics, but at least like you know. And when it comes to WebRTC, that's how I learned a lot of things. Like, for example, the Camera One API is so old that nobody cares about it. But I started seeing crashes, especially during the pandemic, because we grew by like 600 times. So suddenly everything blew up, obviously. And that's where I was like, Crashlytics, okay, topmost crash, what's this? Oh, well, turns out that a method that says is supported, you expect it to say yes or no. And it was yes, no, crash. So, all right.
So
let's
on that point, what's your stance on supporting older Android versions? Because we're supporting Android 8 and up at the moment, but I've started
which one? Sorry?
Android 8, Oreo.
8 and up. I think that's a good baseline.
But I've started really dropping even 8.1 now because Google's not maintaining it anymore.
Yeah. We state support for 7 and up, but that means it compiles, pretty much. And generally speaking, Google has been a lot more aggressive than it was in the past with pushing things forward. With the migration to Unified Plan, we had to migrate to 7. I'm not sure. Google used to have like a sort of unwritten policy on what version it was supported. I think right now, it's API level 2024 or something. So right now, like on the Jitsi side of things, the policy is to support as many as we can within a reasonable effort, which means, because there's also a number of things like devices running old versions are also not very powerful. So they're going to run into issues like, I bought this Android Go thing for testing, which is, even rendering 2 videos is just sweating. So yeah, at some point you have to draw the line somewhere, and I think it's where you find it most comfortable. The plugin will work in older versions, but of course it will always be constrained by CPU usage mostly, I would say. Even though if your specific case, for instance, is like one-to-one calling, so no simulcast, or maybe a small number, you can play around with hardware encoders. Something I think we can experiment with is having the decoder factory do fallback to software. So start with hardware, and then there's a way to make a fallback factory. So we would do, if it's x264, only hardware, because on the native SDKs there is no software x264. And for the rest of the codecs, if there is a codec, try hardware. If we fail to create that decoder, because there's also a limited amount of decoders that you can create, and you don't know that number. If you fail to create one, do software. And for such constrained environments, I think that could be one possibility. The potential sort of unknown here is that if there's rendering issues, you're not going to see them in Crashlytics. You're going to, and I don't really know how you could detect them other than getting reports, right? And because how flexible libWebRTC is, you're allowed to inject your own codecs, which is what Duo and Google Meet are doing. So I'm not sure to what extent the wrappers for the hardware decoders are tested in, like, to this day. Like in the past, they were probably used and tested, but like in all the variety of devices, if they crash, if they start creating crappy output, how are you gonna know? So there's that unknown. But I still think there is value in at least giving it another try. Now that the waters are calm, let's say, and we have added this extra flexibility in the codec factories, I think hopefully later in the year I can give that a try and see if that helps.
Thank you, Wim. I think you got a very comprehensive answer there. Very much so. And of course, part of the community is the shared pain, isn't it?
Yes.
About being in the community. Now, in the interest of timing, I'm going to take just one more question, if there is one, before we switch over to the real-time observability adventures, or adventures in real-time observability. Do we have one other question, or are we ready to go? Oh, there is a question at the back there. Thank you, sir.
Hello.
Yeah, it's working.
I'm just going to speak loud. We talked about the web audio thing yesterday. Mm-hmm. Do you think it's possible to port web audio, like get it to the JavaScript layer, with like especially with the turbo modules? Like the older communication primitives might not be efficient enough to do that in real time.
Yeah, I honestly don't know. I think web audio is very, as an API, it's pretty broad and complex. So building all of that, like all that, you connect syncs and yeah, all of that stuff is reasonably complex. I think something, so for instance, if you want to use the crisp noise suppressor, they do currently supply a patch to allow for audio processing in WebRTC, a small patch, and that's where they inject themselves. I told them to upstream it, so hopefully when they do, we will at least get that. And there's also this way to use manual audio, and then you can decide when you start playing things in WebRTC. So that is currently not exposed. But I think it can be if you inject your own Java Device Manager module, and that is possible to do today. So I think with one extra API that you can inject on the native side, you should be able to do a lot of the audio management on your, in Android's case, like for instance on the Java side or Objective-C on the Objective-C side, and then you pass those along at the native layer to us, React Native WebRTC, and then we will forward those to WebRTC, and then you'll be sort of in charge of that. I think that is how things will go, in a similar manner to how we will do end-to-end encryption, because it will need to be at the native layer, so it will need to happen at that level.
Thank you, Saúl, and let's give Saúl a big ComCon thank you. And just like many other speakers, Saúl is around if you want to go and talk to him personally. We're switching over now to Adventures in Real-Time Observability. We've got Alex Maitland and co. coming up, and we'll be starting that session very, very soon.